Right. Take down the topic rotational motion. So up to power and efficiency, we have discussed up to power and efficiency. Now it is rotational motion. So in this lesson, if you follow through the linear motion, now we are familiar with linear motions very well. So in this lesson, that also is similar to linear motion, right? Actually, they are kind of like the same. You have to apply the same set of equations, but the symbols are different, but the equation patterns and how you are going to apply is the same. The only difference is in linear motion it is moving in a straight line, but for this rotational motion the objects are rotating around a rotational axis. So once you define those angular displacements, angular velocities, then they are going to behave the similar to linear motion equations, right? So let's see what happens when an object rotates. So in the board there is this object. So this is the initial position of the object. Then we have this rotational axis. There's always an axis, rotational axis. It goes through the object like this, right? Perpendicular to the board. That is rotational axis. Then around that axis, this object rotates from here to, let's say, to this position. It can keep rotating, but let's say from here to this position, around this axis. Okay. So what happens is, so we need to measure this amount of rotation. So this rotation, we call that angular displacement, not linear displacement. Here it is an angular displacement. So this rotated amount can be measured using an angle, right? So that angle is what we call angular displacement. So this is the imaginary line I have drawn. That line has moved from here to here. So you can see the angle that it has turned is theta. So that angle theta, we call that angular displacement, not linear displacement. It is similar to linear displacement, but here we call that angular displacement. It is an angle, right? It's an angle. Actually we can measure this angle using degrees, but degrees is not going to work when it comes to equations, vector equations. So we need a new unit to measure the theta. So the scientific unit to measure theta is radian, right? You have to be familiar with radians now. Earlier as well we learned this. So any angular displacement is measured using radian, right? So this is SI unit of angular displacement, right? First just draw this one, then take this down. Theta is angular displacement, right? Then there are some special points that you need to understand. Let's say this line. So on this line there are 2 points I have marked as A and B. So those 2 points I have displaced by to A dash and B dash. So what do you see there? If you think about this point has made an angular displacement theta. I'll say that displacement is theta A. So what is the angular displacement of this point? That is theta. I'll say theta A. If you think about B also moves from here to here. And that also has the same theta, right? That also has the same theta. So theta A and theta B, same. So for any point on the object, angular displacements are the same. So this is true for any point on the object around the rotational axis. Angular displacement, same. then but the distance it travels is not same, right? Let's say this distance is SA and this distance is SB. This clearly you can see that this point moves a longer distance and this point less distance. So SA is larger than SB. SA is larger than SB. Correct? These two are not same, but these are like distances are not same, but angular displacements are same. So that is a very important point that you have to understand. Right. Take it down. Then further, since we are measuring this angular displacement using radians, you need to know these conversions, right? So 180 degrees is pi as in radians. So pi is the radian in radians, right? So we know that pi is equal to what? Pi is equal to, you can say 20/7 or something like that. So this is a number, this doesn't have any units, okay? So pi is equal to 22/7. We know that 180 degrees is a pi. So that is, this is the, we need to know this one in order to do conversions. So whenever you are applying, when you are substituting for angular displacement, you always have to convert that into radians. You cannot just apply angles, right? You always have to convert that angle into a radian, right? Into a radian. We'll see when we are doing questions how to do that, right? Okay. Okay, you can take those down. Then the another one is constant angular velocity. Let's say omega. We call this omega. If it is constant angular velocity, you can just divide angular displacement by time. Angular displacement by time, right? That is only for constant angular velocity. Angular displacement divided by time. Okay, constant angular velocity. Then another one is, let's say constant acceleration, constant angular acceleration. We call that alpha. Usually linear acceleration, we call that simple a. Here we use alpha for rotational angular acceleration. So for rotational angular acceleration, we have a set of equations. So in linear motion, we have four equations. Four equations in linear motion, right? But in angular motion, rotational motion, we have similar four types of equation. So the first equation in linear motion is what? V equals u plus at, right? This is final velocity, initial velocity, acceleration and time. So you can convert this into whole thing into a rotational equation. So everything should be rotational or everything should be angular. So for V we have omega. This is final angular velocity. Initial, we call that omega naught. Initial angular velocity plus simple is linear acceleration. Here you have angular acceleration and time is obviously just time, right? Then what is the another equation? This one in linear motion. So here S is linear displacement, but you need to have angular displacement, which is theta. U omega naught V omega divided by 2 times t. Then another one we have u t plus half at squared. When you convert that, theta equals u is omega naught, t plus half, a means alpha, t squared, right? Then we have one more equation, v squared equals u squared plus 2as. So v squared is what? Omega squared. U squared is omega naught squared plus 2a is alpha, s is theta, 2 alpha theta. So these are the four equations, main equations. You can see they are almost similar to these linear motion equations, right? So if somehow you wouldn't remember one of these, always think about linear motion equation. Then you can convert that into a angular motion equation, right? Right. Take everything down. Take everything down. Then I'll just explain about some units, right? So here, for angular velocity, what should be the unit? So theta is measured in radians, right? T is measured in what? Seconds. So this should be radians per second. This should be radians per second. Radian divided by time. So angular velocity is measured using that. Then if you think about alpha, that is angular acceleration, right? So linear acceleration is meters per square second. But angular acceleration, instead of the distance, what we have now is an angle. So that angle is measured using radians. So instead of meter, just put radian there. So radians per square second. So that's the only difference there, right? So alpha is angular acceleration. You can take those units down as well. So that is measured using radians per square second. Radians per square second. Right. Take it down. And if you have any questions, you can ask me. Right. So we have discussed the similarities between angular and linear motion, right? So you have to apply the same kind of equations. So if you are familiar with linear motion, then angular motion is not that difficult, right? So whenever you don't remember an equation, think about that problem in terms of linear motion, then you can do the conversions, right? Okay, so we'll move on to doing some questions, and if you have any questions, please ask me on the chat box, right? Let's do the first question. First try that. I'll give you a minute. Try that. Okay, so in the first question they ask dimensions of angular velocity. Dimensions of angular velocity. So angular velocity is equal to theta divided by time, right? Theta divided by time. So this theta is an angle. It is just a number, right? This theta, it is just a, you know that theta is something like 22/7. It's just a number. It doesn't have any dimensions. Theta does not have any dimensions. So you can put 1 there. Then t is time. So capital T. So this is t minus 1. This doesn't have length, right? It is not a length. It is an angle which doesn't have dimensions. So this is just going to be t minus 1 to the power. So which one has the same dimensions? If you think about frequency, what is frequency? That is 1 over t. So here t minus 1, right? So both frequency and angular velocity has the same dimensions. Got it? Yeah, correct. So the answer should be first one for the first question. Okay. If you have any problems, use the chat box. Right, then try a second question. I'll give you time. Try second question. So an object rotates with uniform angular velocity 20 radians per second. Uniform angular velocity, right? 20 rads per second. For a time 10 seconds. So this is a uniform angular velocity. So what they ask is angular displacement. So what did we do in linear motion for uniform equations? We just apply S equals ut, velocity times, right? So here similarly, angular displacement is equal to omega t. similar to S equals ut. Okay, so this is 20 radians per second. Time is 10. So it is obvious radians per second times seconds. So we need to get the answer in radians, right? So the answer is 200 radians. 200 radians. So that is the angular displacement. You must put units there, right? 200 radians. So that is the uniform displacement. Right. Then try third question. Third question. A fan with angular acceleration 5 radians per square second rotates. So there's angular acceleration now. Okay, angular acceleration. So you cannot apply this one, right? So if there's angular acceleration is given as 5 radians per square second. Initial angular velocity is given as 0. So that is omega naught actually. What they ask is final velocity, angular velocity. So in linear motion, what did we do? When you get questions, when you are given acceleration, initial velocity, and time, you just applied v equals u plus at, right? So what is the similar equation here? Omega equals omega naught plus alpha t, right? So omega naught, that is 0, alpha is 5, time is 10. So this is 50. What should be the unit? Radians per second. So this is the final angular velocity. Okay, just similar to the linear motion. 50 radians per second. I'll quickly go through these because these are like simple, right? You just have to do substitutions. Can take it down if you couldn't get the answer. Yeah, the answer is 50 radians per second. Yeah, so first one. Okay, then try fourth one. First try that, right? So if you are seeing this on recording, please pause and try that first, right? Then check out the explanation. First you have to try that, right? A wheel rotating at 15 radians per second is submitted to an angular acceleration 5 radians per second square second. Time requirement, angular displacement 100 radian after it is submitted to the acceleration is. Okay. So here we have given acceleration. Acceleration is given. Initial velocity also is given. And then the angular displacement is given as 100 radians. So this is like S alpha and U. Sorry, A and U, right? So when you check these details, so what they ask is time, right? What they ask is time. So when they see this equation, you should remember the equation S equals ut plus half at squared, right? So if you quickly remember that, you have enough skills doing a linear motion, right? Right. So S is theta, U means omega naught, T plus half alpha t square. Theta is 100. That is angular displacement. Omega naught is 15. Then we have time. What they ask is time actually. Plus half alpha is 5. Then we have t squared. We got a quadratic equation. You need to simplify that, right? I'll just multiply the whole equation by 2. So 230t plus 5t squared. Then just divide by 5. 40 equals 60 plus t squared. I'll just inverse places. T squared plus 60. 40 goes to the other side. Becomes minus 40 equals 0. Now you have to factor this one. Factor this one. in order to find time. So this 40 can be written like, how do we written like 10 times 4? You can write that as 10 times 4. So you can factor this one as t squared. This 60 can be written like 10t minus 40. Get it? 10t minus 40. So you get 60 minus 40 equals 0. So instead of 60, I just put 10t minus 40, right? Right. Then take t out, t plus 10. Take minus 4 out, t plus 10 equals 0. Then take t plus 10 out, you get t minus 4 equals 0. So here you can get rid of t plus 10. If you take it, t equals minus 10, right? It is not possible. Time is positive always. So the answer should be t minus 4 equals 0, which is t equals 4 seconds. T cannot be minus 10, right? T should be 4 seconds. So you can reject this answer and take the time as 4 seconds there. So the answer should be third one is the answer. Yeah. You can send me the answers in the chat box, right? Time is 4 seconds there. Okay, take it down, and those who already got the answer, try fifth question. Right, fifth question. A wheel decelerates after applying brakes from 300 RPM to 180 RPM within a minute. So here we have a RPM, right? So that's the another thing you need to learn. So first, so we have a 300 RPM. What does RPM means? RPM means revolutions per minute. If you want, you can take it down. Revolutions per minute. But whenever you substitute these in the equations, you need to convert that into radians always. Okay, so 300. So what is a revolution? So revolution is like one cycle, right? So for a one cycle, you have what? So for a one cycle, one revolution, what's the angle? 360 degrees, right? So we know that 180 degrees is a pi in radians. So 360 should be 2 pi. Get it? So instead of revolution here, you have to substitute 2 pi. You have to substitute that in radians, right? One revolution is a 2 pi. You cannot put 360, cannot put. You have to substitute 2 pi. Right. Per minute means you have to divide. So 1 minute has 60 seconds. So this is a 1 minute, 60 seconds. But you need to write that in seconds. Okay, then just simplify this. 5 times 2, that is 10 pi. Now it is fully converted into radians per second. So 10 pi radians, this is the initial angular velocity. Then you need to have final angular velocity, that is what's that? 180. So revolution means in radians, one revolution has 2 pi amount of angle per minute divided by 60 seconds. Per means you have to divide by 1 minute, right? So 1 minute means 60 seconds. Then simplify. 3 times 2, that is 6 pi. Now it is fully radians per second. Okay. So this is the final velocity. Now we have the initial velocity, then the final velocity. So you should be able to do this quickly, right? When you get a question like this in terms of revolutions per minute. revolutions per minute. So what they say is the velocity goes from 10 to 10 pi to 6 pi within a 1 minute. 1 minute means 60 seconds, right? So what they ask is deceleration. Actually, it is a deceleration, right? This is a large value. This is speed has lowered. So there's angular deceleration. We need to find that deceleration. So to find linear deceleration, we just applied v equals u plus at. Here you applied the similar equation. So the final velocity is 6 pi. Initial velocity is 10 pi plus angular acceleration times the time it took is 60 seconds. 60 seconds. So this becomes minus 4 pi when you take it to the other side, minus 10 plus 6 minus 4 pi, 60 alpha. Then the alpha is minus 4 pi divided by 60. So this is 1 over 15. Right? 1 over 15. We got a negative value because this is a deceleration. Okay. So alpha is minus 1. Pi is 22 over 7 actually. You have to do the simplification because of the answers given. Units rats per square second. Right? Then how do we simplify this? I can roughly say this is like something like 3.14, right? We need to get an answer. I'll just approximate this is to 3. Because this is MCQ, you don't need to get the exact answer, right? You need to guess the correct answer. So I can approximate this whole thing into 3. So we have 3 over 15. So this is 1 over 5 actually. 1 divided by 5 is what? 0.2 radians per square second. Then get the closest answer 0.2. And this is a negative value, right? In the question they asked angular acceleration, but we have deceleration, meaning angular acceleration is actually a negative value, negative 0.21 radians per square second. But if they ask angular deceleration, you should provide the positive value, right? Since they are asking angular acceleration, correct answer should be minus 0.21. So the first answer is the correct one. But in the question, if they asked angular deceleration, correct answer should be a plus 0.2. Got it? Deceleration is plus, but acceleration is minus. Okay. So always think in terms of linear motion equations, right? Linear motion. Whenever if there's a confusion, you can think in terms of linear motion and then get the correct answer. Okay, take it down. Then try a sixth question. A wheel rotates with constant angular acceleration 2 radians per square second. So there's this wheel. It is rotating with this acceleration 2 radians per square second. Is the wheel initially at rest? Initially it is at rest. Number of revolutions. Now they are asking revolutions, right? So number of revolutions after 10 seconds roughly is. Okay. Right. Just apply equation first. So initial velocity is given as 0. So S equals ut plus half at squared, right? So omega naught t plus half alpha t squared. So this one is 0 plus half alpha is 2 rats per square second. Time they have given is 10 seconds. 10 squared. 2 cancels off. 10 squared means 100 radians. So you found angular displacement in terms of radians, but the answer they ask is in revolutions. Okay, revolutions. Now you should be able to convert that revolutions, this radians, into number of revolutions. How do we do that? Revolution means number of turns, right? Number of complete turns. Go back to this one. So we know that pi is 180. Then 2 pi is 360. So 360 degrees means a one turn. So instead of 360, I can put one revolution. So one revolution in terms of radian is 2 pi. Got it? Here I'll just find what is a 1 pi. 1. So this is a 1 radian, right? If you want, you can put the units radian there. So if it is a 1 rad, it is 1 revolution divided by 2 pi. Just divide both sides by 2 pi. Then you get a 1 rad is equal to 1 revolution divided by 2 pi. So if 1 rad is revolution divided by 2 pi, what should be 100 rad? Then multiply both sides by 100. So 2 pi multiplied by 100. So what do we have to do? Basically what you have done is, in order to convert this into number of revolutions, you need to divide it by 2 pi. So once you get used to this, you don't need this much calculations, right? You can directly just divide this by 2 pi. It will make sense once you are used to this. But this is what's happening basically from the fundamental level. So 100 divided by 2 pi is the number of revolutions. Divided by 2 pi. So what is pi? Pi is 22 over 7, right? I'll put 7 up. So this is, no, I'll just put, because we need a approximate answer, I'll just put 3 there, right? Instead of pi, I can put 3 there. So 2 times 3. 150. 50 divided by 3. What is that? 1. For 20 it is 6.6 something. So this is number of revolutions, okay? Revolutions. So the approximate answer is third one. That is a rough answer. They're asking about the rough answer. Closest one is third one. This is the number of revolutions actually. Okay. So here we just found that angular displacement in terms of an angle. Then what? They ask the answer in number of revolutions. So whenever you have to convert that into number of revolutions, you have to divide by 2 pi. So if they have given a number of revolutions and you need to convert that into radians, you have to multiply by 2 pi. Okay. So to convert into radians, you need to multiply by 2 pi. To convert into revolutions, you have to divide by 2 pi. Okay. So this is, from this one you can figure out which one is correct, right? But once you are used to those, you don't need these, right? You can take it down. Yeah, some students have taken the correct answer. Yeah, correct. Right. Okay, so now you are familiar with how to use those motion equations, right? So we saw that they are the same thing as linear motion equations. But the only thing is, instead of a distance, what you have is a angle, right? So that angles, whenever you substitute those in the equation, you always have to convert that into radians. Okay, so everything in meters just turned into radian, right? Because it is rotating now instead of moving along the line, right? Then we need to know uh, a combination between linear velocities and angular velocity stuff, right? I mean linear and angular quantities, right? Then we need to talk about moment of inertia. Moment of inertia. So in linear motion, this quantity, this physical quantity is similar to mass. So for linear motion, the inertia is caused by mass, right? So we have a larger mass, we have larger inertia. Inertia means like reluctance to move, or we can say reluctance to give something an acceleration. So if we have a larger object, meaning object with higher mass, to change its motion, it is difficult, right? So that's why we use mass in F equals ma. But in rotational motion also the kind of like similar, but we are not using mass. It is a bit more sophisticated than that. The inertia in rotational motion is caused not only due to mass but also due to the mass distribution. Okay, so we call that moment of inertia. Just first take down that topic, moment of inertia. The symbol is capital I. So the factors that determine that, not only mass affects that, but mass and mass distribution both. We'll see what it means, right? Both affects moment of inertia capital I. You can take it down. Mass and mass distribution. Mass distribution is where those masses are located and how they are distributed around a rotational axis for that object. So that matters. For linear motion it didn't matter, it's just mass, right? Here you need to think about mass distribution as well, how that mass is distributed throughout that object, right? So for an example, you can hold like a knife, right? Let's say not a knife, I mean from a knife it is much clearer, right? So let's say this is a rod. So if I rotate this rod around this axis, around here, it is easier because the distances to the points on that rod is closer to this rotational axis, closer to the rotational axis, right? Got it? But when you hold it like this, now the distance to particles on the pen, they are at a higher distance. That average distance is higher. Got it? So it is difficult, meaning inertia is higher for that rotational motion when you're holding it from a edge. But from the middle, it is easy to rotate because moment of inertia is lower now. So we now understand rotational motion depends on mass and the distance to each particle, each mass parts on the object from the rotational axis. Okay, so we can we have this equation to find the moment of inertia. Let's say you have this object and the rotational axis. So rotational axis goes normal to this, right? This is rotational axis. So let's say there's a particle here m1 mass, another particle m2, another particle m3. Likewise, there are like a large number of particles that make up this object, right? So let's say the last particle, that is mn, m simple n. Then we have this rotational axis. Then you need to think about the distance to each particle. So here r1, then r2, r3, and this is rn, the distance to each particle from the rotational axis. So moment of inertia around this axis is we call m1, distance to that times squared, plus another particle squared, plus likewise mn rn squared. Got it? So these are the, for all the particles you need to do this, mass times distance to that particle from the axis squared. So in a shorter form we can write this like using sigma. This symbol means sum, right? Sum of all these, that's what it means. So from I1 to n, you can put mi here squared. So you just have to go from 1 to simple n. Then take the sum of all those. From 1, you just have to substitute 1, then 2, 3, 4, 5, 6, likewise up to n. Then take the sum of all those. So the same thing as here, right? So we have written using that this symbol. So this is how we define the moment of inertia. So clearly you can see both mass and mass distribution, how the mass is distributed, affects the moment of inertia. If the mass of distribution is higher, for the same mass, we have a higher moment of inertia. It could be the same object, but depending on where the rotational axis, moment of inertia can change, right? Like the same object, but around different positions, different rotational axes, you have different moment of inertias. Okay, you can take this down, take it down. Okay, so to clarify this further, we'll see for different scenarios how this equation can be applied. So let's say, so the first object we are going to do is point mass. So let's say this is the rotational axis. Even though I'm drawing that like a point, it is axis, right, going through the board. So let's say this here we have the point mass, simple m, and it is rotating in a circle. And the distance to that mass, the total mass, is simple r. So if you think about, all the mass is at a distance simple r. Okay, whole mass is at a distance simple r. So if we add all those values, all those are at a simple r, right? So let's say if you divide that simple m into several parts, all those masses are at a distance simple r from the rotational axis. Okay, so I just took r squared out. Then this whole thing, when you add all these, it is equal to the mass. So mass times r squared. So mr squared is the equation you need to go for when you have to do for a point mass, right? So that is mr squared. Let's say another one. Let's say a ring. The rotational axis goes through here. So you have a ring. So for the ring as well, all the mass of this ring is at a distance simple r. So what should be the equation when you add all those? For this one also, moment of inertia should be mr squared, because you can put m1, m2, you can separate into m1, m2 like that, right? M3. Then if you add all those, you get the mass of the ring times distance is, for all the parts, distance is simple r. So moment of inertia is mr squared for the ring as well. Then you can think about hollow cylinder. Hollow means there's nothing in the middle, right? Everything is at the crust. Let's say a hollow cylinder. Inside it is empty. So all the mass of the hollow cylinder is at the outer edge, right? So the axis goes through here from the middle. Let's say the mass is, then the radius is r, mass is simple m, total mass is simple m. So for this one as well, the distance from the axis to all the masses, you need to get the perpendicular distance, right? Let's say, so this is the axis which goes through here. You need to get the perpendicular distance, normal distance. For all the particles of the hollow cylinder, this distance is same. This distance is same, right? For all the particles, it is simple r. So what can we apply for I? For that also, the mass distribution is same for all three. See that? Because we got the same equation, mr squared. Again, I'll tell you, the distance to all the particles of this hollow cylinder from the axis is simple r. So when you add all those, you get the same equation, mr squared. So for all these three, we have the same equation to find moment of inertia, right? To find the moment of inertia, right? Just take this down, right? Then let's think about a plate. Let's say the plate also has mass m. The radius is simple r. And the rotational axis goes through the center, perpendicular to it. So if you break this into like small pieces, small particles, you can see that mass has moved towards the rotational axis as well. So you can notice all the particles are not at a distance r. So the particles are distributed throughout this whole plate. So all the particles are not at the edge of the plate, like in the ring, right? But the distance to some particles, like most of the particles, has decreased. So the moment of inertia here should be less than for the ring. So for the ring, all the particles were at a distance simple r. But here, these particles has moved, in order to make the plate, has moved throughout the plate, meaning they have gotten closer to the rotational axis. Rotational axis. What does it mean? So that r has decreased. Therefore, this has a less moment of inertia compared to the ring, because those particles had moved closer. Now they are closer to the axis. So in order to find that, we need integration methods. But since you don't have that in the syllabus, you just have to remember this equation. So it is not mr squared. Now it is half of mr squared. So moment of inertia is 1 over 2 mr squared. Now you need to remember that this is for a plate. Okay, this is for a plate. Then we'll move on to a solid cylinder. Solid cylinder, so it is unlike in the hollow cylinder. This is not the hollow cylinder, so there's a material inside, right? So if you can understand, this also is similar to the plate. This also has the same mass distribution, right? If you think about this axis, so for each particle, those have moved, there are particles closer to the axis, right? So for the hollow cylinder we got mr squared, but for this one also we get a lesser value. For this also same mass distribution, right? So it is half mr squared. For this one also it is half. So if you understand both have the same kind of mass distribution, you understand moment of inertia, right? For another way to think about this, I can say like, so this is like a one plate. This is a one plate. Let's say you cut this into like many pieces, and if you like increase the gaps between those pieces, you can make it a solid cylinder, right? Solid cylinder. Still that is the same object. You can see the distance, the normal distance to each particle is the same here. It is same here, right? Got it? Right. Just take these two out. You need to remember these equations. Sometimes they don't provide the equation, so you need to remember for these specific objects. Okay, there's one more object that is important. That is a rod, right? Let's say this rod has a mass capital M and a length capital L. And the rotation, if the rotational axis goes through the center, right? This is the moment of inertia of the rod. We cannot actually calculate this using integration, but you just have to remember the equation, right? So moment of inertia around this axis is 1/12 ml squared. Take it down. Right. So that is the moment of inertia around the center, right? Axis going through the center. Another one, you'd have to think about moment of inertia around the axis going through edge. Remember I told you that rotating from an edge is difficult compared to here. It is harder, right? So we need to have a higher moment of inertia for this case. Now the rotational axis is at an edge. It could go like this, or it can rotate like this. Now this rotating this one is a bit harder compared to this. So we have a higher moment of inertia for this one. Same object, right? M and length is capital L. For in this case, moment of inertia is 1/3 ml squared. 1/3 ml squared. Got it? So compared to 1/12, now it is higher. It is like 4 times high, right? 1/3 means 4 times 1/12. If you multiply this by 4, you get 1/3. Okay? So I is 1/3 ml squared. That is the moment of inertia around an axis going through an edge of the rod. Okay, you can take it down. Okay, so those are like some special objects, right, that you need to remember. There are other equations as well, but these equations, in order to find the moment of inertia, is the right. Then try ninth question. So what they ask is dimensions of moment of inertia is. They are asking about dimensions of moment of inertia. dimensions of moment of inertia. So simply it is mass times distance is squared, right? Mass times distance is squared. So it should be ml is squared. So that is the dimensions of moment of inertia. Mass times distance is squared. So the answer should be fourth one, right? Answer should be fourth one. Take it down. Then try 10th question. 10th question. I'll give you a minute to try that. Right. 10th question. Moment of inertia of a mass 5 kilogram. So this is like a point mass, right? 5 kilogram. And it is attached to a string with 2 meter. Now the rotational axis is here. So what's the equation to find the moment of inertia? Simply mr squared. Correct? Mr squared. So the mass is 5, distance is 2, 2 is squared. So 5 times 4, 20. What's the unit? Kilogram meter squared. Clearly put the units there, right? 20 kilograms meter squared. Then try next one, that is 11th one. 11th one. Give you a minute, try that. 11th one. Right, so in that question we have a ring, right? So for a ring as well, all the masses are at a distance, simple r. So the mass is given for the ring as 10 kilogram. All the 10 kilogram is at the edge. And the radius they say 2 centimeters. 2 centimeters. In meters you need to divide it by 100, right? Then moment of inertia for the ring as well, mr squared. So the mass is 10. Radius is 0.02 squared. So 10 times, so this is 4 times 10 to the power minus 4. So it is 4 times 10 to the power minus 3. So it should be 0.004 kilograms meter squared. Got it? So that's the moment of inertia for this ring. This had a less moment of inertia because this radius is less, right? Then try 12th one. That also is an easy one. These are just to you just have to substitute values there, right? So in the next question you can try that on yourself. Then you have a moment of inertia of a plate. So for the plate, mass is 8 kilogram. Radius is 5 meters. Radius is 5 meters. So for the plate, what's the equation? Half mr squared. Remember? Moment of inertia is half mr squared for the plate. So half is there, mass is 8. Radius is 5. 5 squared. Okay. 4 times 25, 100, right? 100 kg m squared. So that's the mass of moment of inertia for the plate. Okay, you can take it down. Then those who got the answer, you can try 13th question. In the 13th question, there's something you need to think about, right? Those who got the answer, try 13th one. So for the 13th one, we have a plate like this. There's something. So this is the plate. This part is cut off, right? Then we have these points A, B, and this point C. Okay. So through each point, there is a axis going through at each case. So what they ask is, so let's say for A, axis goes through. Then you need to rotate this object around that axis. Axis always normal to the rotational velocity, right? So you need to find which one has the highest and which one has the lowest moment of inertia, right? So for all the axis, it is the same object, but when the axis changes, what changes? The mass distribution changes, right? Mass distribution changes, right? Let's compare the moment of inertias, right? There are some other ways as well, but this is one of the ways. You can separate this into like 3 parts, right? Like this, 3 parts. Then we can say this part is represented by, let's say each part has a mass simple m. It's at the center of here, and let's say that is simple m. So instead of this whole plate, I can say simple m here. Then for this one also simple m here, this one also simple m here, right? Then think about distances. So the whole plate, I just represented that using 3 points. It's kind of like a mass center or center of gravity thing, right? I did that for all the questions. We cannot do that, but for this one you can do that, because you don't need values. You just need to compare moment of inertias. So this is good enough. Okay, right. So if you think about A, B and C, which has the highest moment of inertia? IC has the highest moment, because think about this distance, and this distance. So those are the highest. It has the highest distribution for an axis going through C. Then if you think about B, so that is the closest, right? So these 3 points are closest to B. When you take the average distance for these each points, that is closest to B. So it has the least moment of inertia. Then if you think about A, it should be in between these two, right? It should be in between these two. So this is the order. Here I have mixed that up, right? So here you need to have A, center B, this should be C. So you need to change A and C here, right? So C should be A should be C. This is the order. I have mixed those 2 points. Okay. So the answer should be ACB. ACB, so the answer should be 4th one. Right? You need to think about that. So this is a good question to understand moment of inertia. So you need to understand that around different axes, you have different moment of inertia values. So the axis the object rotates matters, even though it is the same object, right? Then you can try okay, now up to we have discussed earlier, we discussed all the kinetic values. So those are using motion equations. We discussed up to that. Then we introduced moment of inertia. So moment of inertia is similar to mass, just mass in linear motion. Moment of inertia is similar to mass in linear motion, right? So moment of inertia is what relates to whenever you have a question for the rotational motion. Okay, so now we know how to convert velocity, displacement, those into rotational quantities. Then we learned how to convert mass into a rotational quantity. Okay, so mass is related with moment of inertia. Whenever you have an object, it is moment of inertia. So in the next question, 14th question, what they ask is angular momentum. Angular momentum. So all those values also have angular quantities, right? Angular momentum. You can actually try that. 14th question, just read it and try that. I'll explain these using questions, right? So there's this plate, they have given the moment of inertia 8 kilograms per square meter. Then they say it rotates at a frequency 1 over 5. The frequency value is 1 over 5. What is frequency? Frequency is number of turns per second, right? So that is frequency. So for this one, 1 over 5 number of turns rotated per second. That is what this means. Per second is the unit here. So in the question what they ask, angular momentum. So let's say angular momentum is like P. So what is linear momentum? Linear momentum is mass times velocity. So what should be the angular momentum? Instead of mass, you need to put moment of inertia, I. Instead of V, you need to put angular velocity. So everything is converted into angular quantities. Then you have angular momentum. Angular momentum, right? So there's rotational kinetic energy. We have half mv squared. Then just convert that into angular quantities. So for all those equations, you can convert them into angular quantities, right? That's all you have to do. Right. Then I can substitute I as 8. So omega, this is a constant velocity, right? So omega is what? 2 pi divided by capital T. This is theta over time. So to complete one rotation, 2 pi, you need a time period, right? So that time, what we call capital T. So instead of this is 1 over T, I can write 1 over T is what? Frequency, right? 1 over T is frequency. Instead of 1 over T, I can put frequency here. So omega is equal to 2 pi f. Frequency is given as 1 over pi. Pi cancels off, you get 2 rad per second. So that is how you can convert that into a omega quantity, angular velocity quantity. So now substitute it here. You always have to substitute it to radians, right? So this is 16. What should be the unit? 16 kg m squared per second. I didn't put radian here, right? I just used, sometimes if you want, you can put radians. So to identify that, but it is not that necessary to put radians. So you can just put per second here. Then you have kg m squared. So like that, this is the angular momentum. Angular momentum. Then similarly, you can try a 15th question. 15th. Right, in the 15th question, we have circular plate, mass 2 kilogram, radius 10 meters, and the omega is given as 2 radians per second. So what they ask is, so it is rotating, what they ask is kinetic energy of this rotation. So for this is a rotation, we call that kinetic energy rotational kinetic energy or angular kinetic energy. Same stuff, right? Similar stuff. So to find linear kinetic energy, use half mv squared. To find rotational kinetic energy, what do we use? Half. Instead of mass, you can put I, moment of inertia. Instead of v, you can put omega squared. So like this, right? So half, we need to find I. They say this is a plate. So what's the equation to find moment of inertia of a plate? Half mr squared. half mass is 2, radius is 10. 10 squared means 100. So you get 100 kg m squared. Substitute it here. Then you have omega. Directly they have given omega as 2. Then 2 cancels off. 2 times 100, that is 200. 200 joules. This is energy, right? Kinetic energy. So this rotating object has a 200 joule of mass. Okay. So you don't have to like particularly specifically remember the equations for rotational motions. We are having the same equations, right? You just have to convert that into angular quantities. That's all you have to do, right? Then you can try 16th question. For that one also you just have to do that conversion. So work done when an object with 10 kgm, so this is the moment of inertia. So they say that this is rotated 10 rounds, but they haven't mentioned the torque, right? They haven't mentioned the torque there. So let's say 10 round means 1 round means 2 pi in radian, right? So this is 20 pi, so the theta is 20. Actually this is the displacement, angular displacement 20 pi. Actually this should be torque, work done when an object with, this should be Newton meters, right? This we call torque. So this torque is moment. Torque means moment. Remember this equation, F equals ma. So for this torque is what we call, in linear motion it is F, but in angular motion it is called torque. We use this symbol. What is this? Remember this one. Let's say this is the rotational axis. Then you put a force here. So how do you find the torque? Force times perpendicular distance, right? So that is the torque. Because to make a rotational motion, you need to apply a torque, not a force. To rotate objects, you always need to have a torque, or we call that moment, right? Remember moment, not momentum, moment, right? So instead of F here, you have the moment, or we call torque. So instead of mass, you have I. Instead of A, you have alpha. In the question, it should be corrected as with torque 10 Newton meter, right? 10 Newton meter. So this is torque 10 Newton meter, right? Here what they ask is work done. So what's the equation to find the work done? So in linear motion we have this equation, force times distance. So for rotational work, we are rotating now. Instead of force, you can apply torque. That is measured in Newton meters. Instead of S, displacement, you have to put theta there. So this is the equation. To find work when you rotate objects, it is similar to this one, right? Okay, so what's the torque? That is 10. Theta is 20 pi. So we have 200, right? 200 pi. Radian, Newton meter, or you can put joules here, because this is energy. So 200 pi joule is the work done. It's the work done. So basically you are using the same equations. The only new thing here is, instead of force here, you need to put torque. Whenever you see force, put torque there to convert that into angular quantity, right? Angular quantity. Then you can try 17th one. That also is a conversion like that, right? But you need to remember the earlier equations, right, in linear motion before doing the conversion. Okay, those who remember that, you can try that. 17th one. Right. In the 17th, a motor can rotate at 2 radians per second. 2 rad per second under a torque. So this is similar to force, right? Torque 450 Newton meter. Its rotational power is. So we have given torque and the velocity. It is means force and the velocity. So do you remember that equation to find power? We discussed this when we are doing energy and power, right? Force times velocity. So for rotational motion, what should be the equation? Instead of power, you can use torque. Instead of this one, you can put angular velocity. Torque times angular velocity. This is the power. This is the equation we are going to use. Now just substitute. So torque is 450. Velocity is 2. So this should be 900. Actually, this is power. So you just put watts there, right? Units don't change. It's still power. So you can use watts there. So it is 900 watts. Got it? So at least you need to remember those linear motion equations, right? Otherwise, you cannot convert if you don't remember those as well. Then you can just quickly convert that, then you can find it, right? Then try next one, 18th one. You can take this down. I'll give you a minute to try that. 18th. If the power input to the above motor is 1000 watts, efficiency of the motor. So at the last class we talked about efficiency, right? So efficiency is what? Output input times 100%, right? So we have this motor. You put power is 1000 watts. So this is provided as electricity to a motor, right? Then the work done by the motor is 900. Work done by the motor is 900. You provide power 1000 watts. This is the output. This is the input. So that input is provided like electricity, right? Then you gain the mechanical energy. So there's a 100 watts loss. Could be like heat. Okay, so input is, sorry, this should be other way, right? So here you have output, then the input. So output is 900, input is 1000, 100%. So this is 90%. This is the efficiency. This motor has a 90% efficiency, right? Right. So this is the useful power. This is the input power. So this has like a high efficiency, right? Like 90%. Now we have like discussed all the basics of rotational motion. I'll discuss rotational motion at the next class as well. I'll be discussing more complicated questions. So far we have at the next one we have angular momentum conservation. So we have linear momentum conservation, then there's going to be angular momentum conservation. Then there are energy conservations, the same types of problems that you get from linear motion. We have to discuss them, right? We just applied F equals ma in different forms, but in the next part we are applying tau equals I alpha for those questions, right? Okay, so everything is like linear motion. Okay, so far we have discussed, we just introduced angular displacement first. Angular displacement, I'll just give you a brief summary of this. Angular displacement first, measured in radians. So this is similar to angular linear displacement. Then we discuss omega, rads per second. This is v, right? Then we discuss alpha, rads per square second. So this is similar to linear acceleration. Okay, then we got these equations. So instead of that one, I can put this equation, rotational. Then this equation. So I can convert that like this, omega naught, omega divided by time. Then this one, omega squared, omega naught squared plus 2 alpha theta. So you should be able to do these conversions quickly, right? You don't have to write even. So then this one. So S is theta, U is omega naught times plus half alpha t squared. So these are the motion equations. We discussed these. After that, we introduced moment of inertia. This moment of inertia is similar to mass. So once you get that, once you introduce a quantity that is related to mass, then you can convert these equations as well. So let's say then we have discussed F equals ma. Here you have torque equals mass I, A is alpha, this equation. Then if you want, you can go for kinetic energy. For rotational kinetic energy, we have I omega squared. Okay. Then if we have work, for work it is Fs. For instead of F, I can put tau. Instead of S, I can put theta. So tau theta. That is how we find work, rotational work. Okay. Another one, momentum, mass velocity. So mass is moment of inertia, velocity is omega. So that is I omega. So instead of mv, you can use I omega there. Then using all these, there's going to be momentum conservation, energy conservation, those stuff, and applying this equation. Where's that? Tau equals I alpha. Tau equals I alpha. So those are the somewhat complicated questions you will get. The purpose of this part 1 is just to introduce all those quantities. So in the next part, we'll discuss how to apply these in more complicated questions, right? So all the rotational angular quantities are introduced now, and you have done some problems on that as well. Okay, right. Then on the next class, I'll discuss those more questions. You need to revise these again and again, right? Before attending the next class, you have to revise these, right? Then